we're going to be talking about circular motion. Now, have you guys, I'll bring the chat back up. Have you guys talked about circular motion yet? This is like centripetal acceleration and angular velocity and things like that. Or is this brand new? Okay, Leandro's saying not yet. Yeah, if anybody else has something to say, speak up now or forever hold your peace. Okay, actually, I want to ask a question before we start. Have you guys talked about momentum yet? People are saying we had one lecture on it. Is that for... I guess I asked two questions. So that was for the circular motion. Okay, so you've seen a little bit of it. But I guess the new question here, have you guys seen momentum yet? Or is momentum on your test or something? Okay, cool. I'm always curious to see what order the professor does stuff in, because I get a set order. Like, this is unit 1, 2, 3, 4, do these in this order. And then sometimes the professor's just like, we're going to do buoyancy first, which is like, we don't even have a lab on that anymore. Okay, so I'll teach you something that you have seen maybe a little bit of. Because you guys may not have seen too much of it, I'll go a little bit more in depth. You have Newton's laws, but no real math yet. Oh, interesting. Well, hopefully last week's lab gave you some practice on forces. But you'll need a little bit of forces for this week, but not a whole lot. Actually, that's not true. You will still need forces, but less. I'll just tell you. Circular motion, haha. So the first thing that we should know about circular motion is we're using a brand new set of coordinates. Whereas before we had, and you guys should all recognize this graphing plane, we have an x-axis, we have a y-axis. The name for this two-dimensional plotting device is called a Cartesian Coordinates. And they are labeled, you know, if say we labeled these 1, 2, 3, 1, 2, 3, and we had a spot right here, we could identify this spot by using a parentheses, and we say, okay, it's 2 over in x, and it's 3 up in y. You guys probably have seen this like 1,000 years ago, and it might seem like crazy that I'm telling you this, but the reason I'm telling you this is because what we can do is we can take these Cartesian coordinates right here, and we can transform them into what we call polar coordinates. And like before, we can represent a spot, but the way that we're measuring is the distance from the center, and then what we're also measuring is the angle from the horizontal. So if I'm looking at this point right here, I would look at how far away it is from the center, so 2 units, so I would call that 2. And let's say this angle from here to there, and I didn't draw very well, is 45 degrees. I would write 45 degrees. And that is how I would draw a point on a polar coordinate system. These degrees can also be written in radians, so you should be comfortable with both. 45 degrees in radians is pi over 4. You should get very comfortable with converting from degrees to radians. There are equations that are very, very helpful that can help us to go back and forth between these two coordinate systems. So the first one is going from Cartesian to the polar coordinates. So this is, I know the position, that is, I know 2, 3 in my x and y position, and now I want to learn how to represent that in our polar coordinate system. And the way that I'll do that is I can find how far away it is from the center by using Pythagorean's theorem. We can draw a right triangle and we can find out what the hypotenuse is, and then we can find out what the angle is by doing, this should be the inverse tangent of y over x, and that's what gives you the angle right here, what's give you the slope, and that's how you go from x, the Cartesian coordinate system, to the polar coordinate system. Very, very important. You can also go backwards. So let's say you don't know what it is in the Cartesian coordinate system, but you do know what it is in the polar coordinate system. And now I'm going to go backwards. So say I know the r, which is 2, and I know the degrees, the angle, which is 45 degrees. You should recognize these right here. I can find the x position by doing r times the cosine of theta, and I can find the y position by doing r times the sine of theta. This is sort of what we were doing 2 weeks ago, and we've been doing this a lot. Trigonometry, you can just find that part of the triangle. And then you can represent it in your xy coordinate system. I guess this is written right here. So this is very, very important to know how to go between one coordinate system to the other, because a lot of the problems might be given to you in an xy, and you need to do them in an r theta, or vice versa. Are there any questions on that before I move on? Sweet. Because now that we have this basis, now that we know how to represent positions in a polar coordinate system, we're going to go back all the way to Unit 1 and 2, and we're going to talk about kinematics, aka the motion of things and how we can describe them. So whereas before, when we had polar coordinates, or Cartesian coordinates, we would call them like distance, which, you know, could be either x or y. Then we had velocity, which was, you know, the time derivative of either one of those. And then we had acceleration, which was, you know, the time derivative of the velocity. Instead of the x and y, we have the r and the theta. We saw that on the last slide. But we also have something new for the velocity, and that's called the angular velocity. So what this is telling us is if something is starting at, let's call this in our polar coordinate system, this starting at 3, 0, because it's 3 away from the center and it's at 0 degrees. And let's say after some time, it is now, and let's say it takes 1 second, it is now at 3, pi over 2, or 90 degrees. The speed at which it traveled from this position to this position right here is the angular velocity. And we use, it looks like a W, but it is the Greek letter omega. And this is just like the comparable thing. We can calculate the instantaneous by doing the derivative. If we have an equation for our theta, we can find out what the equation for our angular velocity is, our omega. Or, you know, we can find the average omega if need be. All the same things that we did before. Similarly, there's also the acceleration, the angular acceleration. Now, here's the really confusing thing, because these characters look almost identical. This right here is an A, the Latin alphabet letter A. This right here is an alpha, the Greek letter alpha. Whenever you see alpha, it is the angular acceleration. Whenever you see A, it is the regular acceleration. Be very, very careful and pay very, very specific attention to this. And we're actually going to talk a little bit more about this in a second, just to drive it home a little bit more. So just like before, where we had our kinematic equations, we can transfer them to the angular versions of them. So the four equations, well, I guess these equations should look very, very familiar. We did them in Unit 1. They can be written in terms of our angular, our polar coordinates, and they're basically the exact same. And then this right here is our quadratic equation, the one that describes position, and we can also use this to describe the angle. So if we know what the initial position, initial velocity, and what average angular acceleration something has, then we can figure out at any time how far it has traveled as far as the angle goes. I'll erase these and I'll pause for a second in case you want to write them down. They are on your sheet, but you know, they always say that writing things down is the better way to learn them. So I was mentioning that there is a big difference between the angular acceleration and the regular acceleration. We have to be very, very particular about our language right here. Whenever you see a Greek letter that's either omega, theta, or alpha, we know that we are in polar coordinates. If we see X, Y, or Z, if we see a Latin letter, that means we are in Cartesian coordinates. Or we might see something called radial and tangential. Now, tangential speed, if say we have a wheel and there is a bug that is clinging to the edge of this wheel, and this wheel is spinning. At this instantaneous moment in time, the bug, and here I'll draw it more like a bug. Look at it, so cute. Has an instantaneous tangential velocity or tangential speed. And a lot of times we write it as Vt for V tangent. Be very, very careful about this. This is not equal to omega. But there's a way that we can find V tangent from omega, and that is by this equation right here. So the tangent velocity is equal to omega times r. So it does depend how far from the center something is. So if our bug was like way out here on like an even bigger circle, its tangential velocity would be so much bigger. Similarly, there is a tangential acceleration. And this does not need to be in the same direction as the velocity. So for our example, we're going to have it go backwards. So our tangential acceleration in this situation is backwards. So if you look at this and you think about physically, it's moving this way, but it's accelerating in this direction, which means the wheel should start slowing down until eventually it comes to a stop and then starts going in the opposite direction. If, for instance, the acceleration was going in this direction, the same direction as the tangential velocity, then it would be speeding up. The tangential acceleration can similarly be described as alpha, which is our angular acceleration, times r. So same thing as we saw before. Now, here's the really important part. And if you're going to pay attention to anything in this lecture, it's this one right here. There is a second acceleration at play. And this one is always at play. If something is moving in a circle, the radial acceleration is happening. Let me say that again. If something is moving, I can't see that. If something is moving, there is a radial acceleration. If something is moving in a circle, there is a radial acceleration. If something is moving, there's a radial acceleration. Because even if something has the same speed, it's traveling at, I don't know, let's call this 10 meters per second here. After it has traveled over here, and we have our bug that's now on this side, it's going here, still at 10 meters per second. But the important thing is it has changed direction. And, you know, if it's right here, it's changed direction. And anytime your velocity is changing direction, that means that there needs to be an acceleration. Full stop. If velocity is changing either in magnitude or direction, there's an acceleration at play. And because this thing is staying on a circle, the acceleration is always towards the center. So at these three different spots, the instantaneous radial acceleration is always towards the center. So let me erase the velocities just so we don't get confused. And this equation, you're just going to have to know. This is, so the radial acceleration. And oftentimes you'll see this right here. Sometimes it's called centripetal. You'll have to be able to know that these are the same words. The radial acceleration is equal to the tangential velocity squared divided by the radius. We can write this another way. We can also write it as omega squared times r. These are the same thing. You can use it in either way that you want. But we have to know that the radial acceleration will always be pointing inwards towards the center of this object. And it is related to the tangential velocity squared divided by how far away it is from the center. Technically, you see how this is still a Latin letter. This is still an A and not an alpha. This is also an A and not an alpha, which means we can combine the two, and they are the same acceleration. So if I just write A, I can use Pythagorean's theorem, and I can do the tangential acceleration squared plus the radial acceleration squared, which, you know, if I plug in my values here, I get alpha squared r squared plus, and if I take this right here, you have to be careful. You have to do it twice. You get omega to the fourth times r squared. There's a couple other ways that you can write it. You can write it like, if you just know what the tangential acceleration is, you can just leave it as at squared plus v to the fourth divided by r squared. And then you take the square root of it. Don't forget to do that. When you have both a tangential acceleration and a radial acceleration, your total acceleration, and this is straight up just an answer to one of the questions on this problem, or to this lab right here. So you have a bug, and there is a tangential acceleration this way, a radial acceleration towards the center, as always. Then if you know how to add these vectors right here, you could just move this line to be here, and then draw a line right here. So let me make that a little bit more clear, because that's messy. Oops. The acceleration, the total acceleration, is going to point between these two. There's a question on this lab report that's going to ask you to draw a picture that is very similar or practically identical to this. So yeah, make sure you get it right. The last thing that I want to say, because I don't think I emphasized it very well, is that when we're counting like positive versus negative, because direction usually matters, right? For our Cartesian, we had positive y and then negative y. We had positive x and then negative x. In our polar coordinate system, we don't really have a negative r. A negative r, so if this is positive r, then a negative r is just a different angle. So you can represent a negative r just by adding 180 degrees or plus pi to whatever angle you have. So not really a negative r, but we can have a negative theta. And what a negative theta is, well, first of all, we always measure from the right-hand horizontal. I don't know why we do that. It's just the convention. Sometimes you will be asked to do it from the vertical, but very rarely. Positive theta is in this direction, right here, going counterclockwise. Negative theta is going the other way. And as you can see, a positive theta can always be written as a negative theta or vice versa. So if something is right here, I could label it as negative 45 degrees or as positive, I don't know this off the top of my head, 325? No, 315 degrees. However, note that if something travels, let's say it travels here and then goes all the way around to here, but went around twice, it would be 315 plus 360 degrees. So I don't know, whatever that is, 675. It has traveled a total of 675 degrees. That might be important for some of your questions. But that is all I have to say for the chalk talk. I'll pause again real quick in case anybody has any questions. This right here. It even gives you a warning, something about browser compatible version, Sim is not compatible with iPads, blah, 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 blah. If you try and run the simulation in the browser, you can do it, but you're going to be fighting with the simulation more, if not the same, probably more than you'll actually be doing the lab. So what you should do, and you can either Google this yourself or you can follow me, you can download the Java version. So if you click on it, it will have something called rotation_English.jar. You can save it to your downloads folder or wherever you want. It doesn't really matter. Yeah, if you figured out how to do this last week, you can do the exact same thing, except for this one, it's like recommended highly. You can download that. And then if you have Java installed on your computer, you can double click it and run it. For my computer, it doesn't work like that. If you don't have Java, just Google Java, download it, install it. Word of warning, you might want to like double check the manual install because sometimes it like changes your search bar or whatever. If it doesn't run automatically by double clicking on it, you can run it from the command prompt. If you don't know how to do that, talk to me. I will walk you through it too. But I really, really highly recommend that you do it this way. Otherwise, it's just going to suck. You will find it right here. It's kind of cute. There's a ladybug. There's a beetle. The introduction tab will allow you to pick up the ladybug, place it wherever you want. You can pull out a ruler to measure how far from the center it has gone. This sliding bar right here will show you the angle that it is currently at. And as you can see, as I'm moving it around, you can see acceleration and velocity vectors. Do we have to throw the ladybug into walls? That is not the intent, but that will probably happen. So yeah, you can sort of see like what's going on here. You can see that there is the acceleration and the velocity of the ladybug as it goes around in a circle. Note that these are the Latin letters A and V, not alpha and omega. So these are Cartesian coordinate systems right here. You're going to play around with this like for 2 minutes, and then you're going to go to the actual lab, and it looks awful. So here's the first word of warning. If you're placing things on the simulation, that will start the simulation, which is dumb, because you're going to have to place it at places sometime, and you'll see that the graphs are going. Once you get in the place that you want, hit stop, clear, and then you can start from wherever you're going. The important things to know here are the differences between degrees and radians. There are ways to switch between the two. Make sure you know how, because you will be using both. There are 4 different sets of graphs. And again, you're going to need to be very familiar with what they are. The first one is theta, omega, and then an x and y graph. Remember the theta up here is the actual angle. The omega down here is the angular velocity. So if I set this to 10, actually, let's do this in degrees. If I set this to 10 degrees per second, and then I start the simulation, I will see that my ladybug is moving at an angle of 10 degrees per second, or an angular velocity of 10 degrees per second, which is super slow. I can set my initial angle, so I can set it at 90 degrees or 45 degrees or whatever I want. You can also see where it is in the x and y coordinate system, which I'm going to give you guys another answer here. Say this is 120 radians per second, or degrees per second. You'll see that the graph that is made by the x and the y graphs, and I can just show the x or just show the y. These are sines and cosines, right? And you should recognize them because they have to do with circles. Sorry, my cat. And that's where these come from. That's where sines and cosines come from, is things moving in circles. Another graph. This is theta, omega, and alpha. Remember, alpha is the angular acceleration. There's a similar one at the bottom that's theta, omega, and a, which is the total acceleration. Don't get those too confused. And there's also one that's theta, omega, and v. And remember that v is the actual velocity, the Cartesian velocity. These are the tools that you will have. Make sure you're being very, 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 very careful with which graphs are showing, what values you're taking, things like that. You can read the information by dragging the gray bar back and forth. So if I have run a simulation for a while, I can move this back and forth at different times. And that's the simulation. I don't think there's anything else I need to say. Yes, there is one more thing I need to say. It usually doesn't matter what units you're using for the angle. Degrees and radians are usually interchangeable. But if at any point in time you have to multiply by something that uses meters or kilometers or kilograms or whatever, if it's using an SI unit and you're multiplying or dividing or adding or whatever, you have to use radians. I don't know if that's going to come up in this lab, but just good to know, because radians are the standard instructional whatever, the SI unit for angle. So be careful with that if it ever comes up. But that's all I need to say.